Welcome to this JuliaCon session. Luca Ferrante will be the chair for this session. Our first speaker will be Guilherme, and he will talk about the debugging time spent in LLVM with SnoopCompile. Please join me in welcoming the speaker with a warm applause.
Oh, thank you very much. I think you can hear me well. So today I'm going to talk about measuring the debugging time spent in LLVM with SnoopCompile. A quick introduction, I work at a company called PSR, and we do a lot of energy modeling, and we are heavy users of Jump and Julia since 2016, I think. And so, well, we do a lot of advanced tools for energy systems, and we are currently doing like many production systems in Julia. And some of our clients use some operation planning, generation expansion, portfolio optimization tools written entirely in Julia and Jump. And each one of those tools has evolved over time, and some of them have more than like 80,000 lines of code. The other ones have like 40,000, which are kinds of big applications in Julia, in my opinion. And they started a long, long time ago. And so when I got to PSR, some of those applications were already mature enough and developers were there for a long time. And there has always been a complaint about time to first run of those tools, especially when developing. Because when we deliver this to our clients, we usually only use package compiler. And at the same time, well, this problem is limited to developer experience. And for developers too, usually you just turn on revise, or you run Julia with some tricks in compilation. You turn off the optimizations, and you compile the minimum amount of code possible. So it's quite fast to deliver and to develop using those tools. But it was always something that tricked me. Like it annoyed me so much that when we run with the standard compilation and optimization switches, it took some time, like 3 minutes, to have the first run. And then I started my journey with SnoopCompile, and the first flame graph that I plotted was something like this, where you have like this huge blob in the left, where I'm pointing to, your right, probably. Yeah, no, your left. With the type inference, this like huge valley, which is LLVM time doing compilation, and this small other inference time at the end. And so I started digging into the code, and digging into the rabbit hole, I found a lot of type instabilities that have been there for a long time, and some unnecessary specializations. So one example of it is that we had a function called open. I changed a little bit the types, but the idea of the function is this one. And this open function was specializing for 300 different functions. And it was taking about 11 seconds only to like do the inference on these functions. And this sucks. There's a lot of time spent, and like it annoys me so much. And so with some small adjustments, we got like a no specialized wrapper into the function and things like this. We come around to like, instead of 3 minutes, now it's 2 minutes 30 in the same case. But even with some other ideas in mind, I decided to try to dig deep into it and see if I could measure the time spent in LLVM. And then I searched into a random issue in SnoopCompile, and I found that this macro existed already. It was not just that well documented, but there is a snoopl macro that allows you to measure exactly the time spent in LLVM. And this is the goal of this talk, is to bring the attention to everybody that you can do this and you can measure the time. And so, well, it's a very simple script. It's a very simple way of doing it. You just call the snoopl function, and you pass these two files, these func names and LLVM times.yaml. I run all two. I changed a little bit the name of the package because it's a proprietary software and I didn't want it to disclose everything. And well, when you run this, you gather these two files, and with this very small script, you can understand exactly how much time each function spent only compiling the LLVM code, only doing the LLVM step. And then the first time that I did this, I saw a lot of functions that were spending more than 1 second only to generate the LLVM. In particular, there is this one function that spent 10 times only generating everything. So this is a big red flag that something's very wrong with the design. And then it took our attention, and we started to do a bunch of refactoring. And most of the parts that spent a lot of time in LLVM is just that some functions were like 1,000 lines big, which makes no sense. And you should follow the performance tips in the Julia documentation. And we still have some more than 1 second LLVM times in this situation, but like right now it's much better, and we really put some thinking into it, and it's really possible to redesign your code to be more type stable and to spend less and less time into inference and LLVM. And right now, for this particular model, the time to first run is 1 minute 15, but like it annoys me less right now, and we can still improve it. We have new hires, and some of them are working on this. And well, as I said, the goal of this talk is just to like point it that if you're having time to first run, time TTFX, you can go one step further and don't stop at inference and go to try to measure LLVM times. And sometimes it is a very direct search, because it points me directly to the method. Like this method in particular is very, very bad. So that's the main idea and main advantage of this tool, that I think it's not that well advertised for the community. And so my conclusion is this: well, the snoopl is a great tool to understand where your code base might be not healthy. It's a great indicator where you have like pain points in the code base. And we use all the tools described in SnoopCompile, the snoopl to measure all the type inferences. You use snoopl to go down into the inference calls and understand the type stability of the code. And this is really, really helpful. And well, you should definitely follow the performance tips written in the Julia documentation. That's the talk. Thank you very much.
Yeah, thank you for the talk. We have time for a couple of short questions, if there are any. Yeah.
How actionable is that output? I'm not used to digging into LLVM, so that name at constraint 2 doesn't mean anything.
No, it actually is exact. Now it doesn't mean anything because I changed the name, but it is like it's actually the name of your function. It's Julia underlined the exact name of your function, and it's very easy to dig into. And like as soon as I saw the 10 seconds, I said, "Oh well, obviously this is yes."
That is measured all of LLVM or primarily the code generation to LLVM? And how useful or would you want to expose timings at like LLVM pass level?
Like I think this is only the LLVM pass levels. Because in the YAML file it has like the number of code blocks at the beginning and the number of code blocks at the end. So this is only the time spent in LLVM optimizing. It's not the code generation. I think the code generation for the code was fast. I mean, it helps every time that you have more information, but I was happy with this analysis. I was pretty happy.
Do we have any other questions?
How can you choose which functions to soup, and would it be useful to have a tool that could soup the implementations?
Like in our particular tools, like since we package compile, most of them we have a single entry point to a path. Or a folder with a bunch of files, and then we just chose this one and it propagates inside, so it can measure anything that gets called inside. So in our case it was an easy decision because we only have one main entry point for the whole application.
If there are no further questions, let's thank the speaker again.